Hello and welcome to Calculus 1 more particular. We are going to talk about limits, introduction to limits as a concept. So we mentioned last time that calculus consists of three parts: limits, derivatives, and integrals. And limits are used to define and explain both derivatives and integrals. So it's natural for us to learn those first, even though that was the last one precisely defined and explored to its gory detail. So derivatives were discovered first by Newton. He did just a tiny speck of integration, but then followed integration and then limits at the end. And today in modern education, quotes on the modern, we explain limits first, and then we go with derivatives, then integrals. So what is the limit? Well, precise definition, funny enough, for limit is going to be in the last section of the chapter. So chapter 2, section 2.7 is called the precise limit of definition, and that is where you learn the definition of the limit. So prior to that, right, we're going to use what I call a street definition of a limit, which gives the description, to some extent, and it's not mathematically rigorous, but it's very close to what you are already used to. So in some sense might be very, very useful to learn the limits this way without jumping immediately into, theorems and definitions, at the beginning of the calculus course. So starting with the idea here, I'm going to say that your definition for the limit, what I refer to as a street definition for the limit, is limit computes y value of the function. So limit computes y value of the function. So that's what we have. So now, when you think about that, we have the exactly the same thing that's happening with functions, right? From pre-calc 1. If you have the function f of x equals, let's say, x squared minus 3, and you want to compute f of 4, that's just going to be 4 squared minus 3, which is 13. And if the limit computes the y value of the function, you would actually write limit of x squared minus 3 as x goes to 4, in this case, is also going to be 13. So there's no difference in answer, as you can see, but in this case there is a lot of difference in a way you obtain the answer. I'm not going to go into visual. Yeah, this one is just, this looks this way and the other one has word limit in it and so on. I'm not talking about that. I'm talking about the actual way you obtain 13. So, and there are two completely different approaches, which in some cases give us the same answer, and in other cases it will give us different answers. So let's take a look at first the way to calculate this 13 using the graphical approach and what's happening behind the curtain. So if I can draw straight, there we go. If I have the x squared minus 3, so that's going to be a function that dips below and goes through negative 3 over here. And then I want to compute what's happening at 4. Let's say this is where the 4 is. With 4, you would go up, and wherever you hit the function, you would bounce off, and then that will be 13. So this point here is exactly for 13. Your 4 is the input on X, and the 13 is output on Y. And this is the standard, right, thing that you know from your pre-calculus life. But now, and that's that method of plug in the number, right, and just follow PEMDAS computation rules to compute the value of the function. And if you change the location, obviously you will change the answer. So if I want to calculate at 0, then I plug in 0 and I just get -3, which is 0, -3 as a point, which is on the y-axis. But the goal over here, not the goal, the thing that we want to know here is that you plug a number in, you compute the number, and you are done. Limits don't work that way. Limits compute the value of the function at all points close to 4, around the 4, but they never compute at 4. So it's a complete inverse of what you have with this situation here. So let's go and go here and take a look at this. So I'm going to draw again. This is my function, this is my y-axis, my x-axis. And I'm going to pick, let's say, 4 to be right here, which would give me, I'll do this lightly, which gives back this 13. This is the old stuff. Now, what is the way that the limit approaches the problem of find the limit x squared minus 3 as x goes to 4? Well, see, the limit has this idea of approaching 4. Approach, walking, right? So you approach something by walking towards something. So now there are two ways that I can approach 4. I can approach from the left, and I can approach from the right. Now that is me literally walking on x-axis and getting closer to the location labeled 4. Or on a highway, as you drive, there is exit 4, and you have mile markers that are approaching that number. So they're increasing or decreasing into it depending which way you're going. But the fact is that you are physically approaching, meaning you're picking x values that are always closer and closer to 4. Now this motion on x-axis, as you are picking points closer and closer to 4, let's say in a red set, translates into a motion of these answers going up this line, which translates on the y-axis going to up to 13. And from the blue side, from the right, you have exactly opposite. So these guys collapse at 13 from both sides, and then they agree that the answer is 13. Now, much better way to understand this is to use the table of values and portray red and blue side, which I call Romeo and Juliet, where Romeo is blue and Juliet is red, because we should uphold those stereotypes, obviously, right? So as you approach from the left, it's going to be red, and those numbers are going to go, the x input values are going to go up, and then the blue ones are going to go down, both of them towards 4. So let's pick our values. I'm going to make the chart. I'm going to put my x values here. That's a 4 that we are going towards, and the y value here, and let's pick some numbers. So chart is set up, and now I want to pick from the red approach numbers that are smaller than 4, but they go towards 4. Now it's not good to use 1, 2, 3, because those numbers are really far away. I mean, any number is far away because you can put infinity in between any of the two numbers you can think of. But Let's go with for the concept over here with 3.9. So if you want to think of the 4 as a $4, then this is $3.90, and then $3.99, and then $3.99, right, which is the what you pay on a gas station if you never paid attention. They give you the price of gas, and then they put 9/10 on the end. That actually stands for a tenth of a cent. We don't actually have use for cents. They cost more than their value now to be produced, so they should be discontinued, right? But the gas station, for some reason, has a 9/10 of a cent. So make sure you ask for change next time you're at a gas station, because I don't think that those tenths of a cent are adding up to a round cent at the end. Anyway, you have all of this, and that's the approach from the left. Those are the red numbers. Now the blue numbers, you're going to go far at 4.1, and then 4.01, and then 4.001 as you are getting closer to number 4 from the right. So numerically, these values are going right up for red, in this case, up for red and down for blue. Now you pick up your abacus and you compute these values in x squared minus 3. So your function here, right, your limit of x squared minus 3 as x goes to 4, you are computing the red values in the formula and writing all of the red answers. And then on the blue side, you're doing the same with blue numbers. So we have to compute now 6 of these and plug the values in. So we have 3.9 squared minus 3, which gives us 1221. So we are working on the red side, 1221. Then you have 3.99 squared minus 3, and that gives you 12.92. And finally, you have 3.999 squared minus 3, that gives you 12.99. So I hope that you see that this trend is the numbers are rising, and they are rising towards 13, right? Because the last number did not jump over 13. It got closer to it. So we go from 12.2 to 12.92 to 12.99. Now, if you really want to push this, go ahead, 3 point, put the 4 nines there, do the calculation. Put the 5, put 6, put 7, and you will see that all of them fall in a line. All of them fall in a line, and you will never reach 13 actually from this side. So you are going to just keep going with these decimals, and the more decimals you put in, obviously, the closer to 4 you are. The more nines you put in, the closer to 4 you are. But you will see that the y values will never cross to the other side. Now, on the other side, we're going to start with 4.1 squared and subtract 3 to get 13.81. Then we're going to have 4.01 squared times, sorry, not times, minus 3. And that's going to get 13.08. So you see how you kind of lost 85 cents, close to 85 cents. No, 75 cents away. So, you know, it's getting closer to 13. The number is going down. Let's check 4.001 squared minus 3, which gives 13.008. That doesn't even make a cent, right? And you can see that these numbers are falling down to 13. Well, if it walks like a duck and quacks like a duck, it's 13, obviously, right? So the answer is 13. You have to notice that limit never computed at 4. limit computes the values at infinitely many points around the point you're interested in, and it never computes the point you're interested in. The point you're interested in, pre-calculus computes that point. So pre-calculus would just compute there and give you answer 13. Limits are going to compute at infinitely many points around 4, never computing at 4, and then give you the same answer of 13 because both sides would hint that 4 should be at 13 because all of these numbers fall in line and they kind of point right towards 13. Now you might be thinking, what is this nonsense? Like, why do I need this limit if I could just quickly plug in the number that I actually need and be done? Okay, you have that in pre-calc, and I guess that's it, right? You're done. For those of you who want to understand calculus, you're not done. There is a huge advantage in certain cases if you do the limit. And that case is if the value is not present. So if I had a function that had the open circle like this at 4, right? And you had your graph. Pre-calculus now for f of 4 would have to say does not exist. DNE. It has to say does not exist because, right? Because the value, the y value is not there. So when you go from 4, you stretch up, it just passes through the point, never bounces towards the y value. In this case here, the limit of x squared minus 3 as x goes to 4 would still give you 13. And you would say, well, that's pointless because the point is not there. Why would you even want to know? Well, that's a valid question. And I'm going to say, well, how about a bridge that has one part of the bridge collapsed? This is the actual way you would approach to fix it. So if I draw this riverbank over here, right, and then you have a bridge that goes across. Let's put some support for this bridge on the sides. There we go. What I'm going to do is I'm going to make one part of this bridge out. There we go. So now bridge is broken there. Right, this is your standard bridge, right? It has the the whole thing that you are used to seeing on the bridge. Whatever it is. Okay, the tablet looks like it's starting overheating, so maybe I should get that pad before the break. But anyway, here is the part of the bridge that it's missing. Here's the water, right? The cars would drive this way over the bridge, right? There's another car. Let's make this sports car. Put that fender over there, the wing actually. Make that. There we go. Perfect. So these cars are coming onto the bridge, but there is this one section of the bridge that collapsed and it's in the water. So pre-calculus literally says, yep, it's broken, and that's it. It's the end of the story with pre-calculus. It's broken. Done. Calculus says we approach from the left. We approach from the right. And we are actually able to fix it because we know what elevation of bridge, that's your y value, we know what elevation of the bridge is missing, and we can compute that value, and we know what we have to, and you physically approach from two sides. So this would be known as a two-side approach, and in many cases is as simple as you're just getting the y value of a function. That's all it is, right? Y value of the function, not a big deal. But we actually do a little bit more than that when we compute the limit. So I gotta get this cooling pad because it is the tablet really slowed down, and I can't believe that it overheated so quickly. So I'll be right back. All right. So what we have is the situation now where we have another way to compute value of the function. This one has a lot more work to it, obviously, because you have to compute infinitely many values around the value you're interested in. But the advantage is that if the point doesn't exist, the one that you are computing at, well, in that case, right, you can still compute because you never compute at that point. You compute at all other points around it. So now we have this idea of the two-sided approach. Come on, line. There we go. So two-sided approach where for the function, let's put any good old function there and pick a value right here, call that value a. It's the y-axis, this is f of x function, this is the x-axis. We are going to have the approach from the left. So approach from the left, and that's going to be a limit x goes to a minus. This minus is like in a superscript, like a square or something, of f of x. That's the approach from the left. Then we have Romeo, approach from the right, and that's going to be the limit of f of x as x approaches a plus. That's the only difference, this little minus and plus in the notation, and that tells you which one, right? Both of them. Now, those two combine into overall limit, and we have a theorem for it. So I'm going to say when those two give us the same answer, then limit x goes to a of f of x is that answer. Which should make sense, right? Think about it. When you bounce this off into the y-axis, the blue one drops down, the red one rises up, and they together meet at the value L. So now we get to our first and one of the most important theorems of Calc1, because again, this is used to define your derivatives and integrals later on, so technically the whole course. And that theorem is going to say that if the limit x goes to a minus of f of x is the same as the limit x goes to a plus of f of x is equal to L, then the limit x goes to a of f of x equals to L. Well, that's what limit exists, and it is equal to L. Otherwise, meaning if they're not equal, otherwise limit does not exist. That's it. So if limit from the left and limit from the right is the same value L, then so they agree, then your limit is L. Otherwise, limit does not exist. And we can show that on example, one of the favorite examples, y equal 1 over x. So you're supposed to know this function, memorize this function from your pre-calculus course. It is a function that has two parts that go like this. And now I'm interested at limit x goes to 0 for 1 over x. So what's happening there? Well, to solve any limit, what you do is you take the, I'm going to fix this. You take the left approach and right approach, so Romeo and Juliet. So first let's talk Juliet over here. So Juliet approaches this 0 from the left, and her y value goes down to negative infinity. Romeo approaches 0 from the right, and his value goes to positive infinity. So technically, by approaching the same location, which is 0, they went infinitely apart, because she went down, he went up, and they are infinitely apart as they approach 0 in this particular example, right? And we all know what happened in the book, right? As they approach to the same location, they just like, it's better just kill ourselves, right? It's just whatever, billions of people on the planet, and the right one like lives right next to you. You know what I mean? Stupid teenagers. But anyway, when you go this way, we have to take a look at the limit approach from the left. So limit x goes to 0, and we put the minus to say from the left of 1 over x, and that's going to give us negative infinity. And then the limit x goes to 0 plus 1 over x is equal to positive infinity. They are not the same, so that gives us that the limit 1 over x does not exist, right? So x goes to 0. That limit does not exist in this case because they did not agree. Now, previous example that we discussed, right? Previous example, they agreed. Both of those values went to 13, and they were perfectly able to meet at height 13, which I guess was the earlier in the book with the balcony thing, right? So that's probably that thing. So that's the story of limits. I hope you're not disappointed, because literally that's it. It's the y value of the function. You are picking up the values of x, going towards the value you want to observe, and you are computing that value. You are computing that value there. Now that is achieved by left and right approach, and then if they match, you're good to go. If they don't match, right. Now the other way to have this not match, that it doesn't have to be infinities. You can have a piecewise function where there is no limit at the value. So you can have a piecewise function, let's say, look like this. You have this linear line, and then it jumps here, and let's say it's parabola afterwards. This is all one function, which would have those multiple lines. We can actually write what these are. If we say that this is 3, this is my f of x. This is all f of x, right? It's all f of x. We can actually figure out by looking at the graph what this function is. It's going to have two parts, because this piecewise function has a part that it's smaller than 3 as linear, and part that is larger than 3, which is parabolic. So the linear part, let's say that this goes through, maybe I can angle it better. Let's angle it better to go through. And now I made it. Now I made it 45 degrees, whatever. Goes through 1 right there. So this is going to be x plus 1 for all x values smaller than 3. So that's my domain, right? And then we have this one to have the vertex, right? This vertex here is 3, 2. This vertex here is 3, 2. So now what you do is, this vertex is 3, 2, and you can use that in the equation. If you remember the equation from a pre-calculus, when y was equal to a x minus age squared plus k. This is your age and k, so you can just plug in 3 and 2 in this formula, get a x minus 3 squared plus 2, right? And then all you need to do is to figure out what a is, because if you know the vertex, and you just need to pick one more point, pick this point over here. So that's what? That's 6 and 1, 2, 3, 4, 5. You plug in 6 and 5 for x and y, whatever, right? It doesn't really matter. Let's put y to be 1. I don't care. Say a is 1, whatever. We will have x squared over here, minus 6x, and then 9 plus 2 is 11, and that will be for x larger or equal than 3. That's it. So this is the function that we are able to write looking at the piecewise. This is again pre-calculus skill, because we are dealing with polynomials, and the amount of these breaks that you are going to have, like pieces of a function, will be the amount of separate lines that you have to have. Now, if I want to find limit at x goes to, let's say, 0 of this f of x function, well, that means that here is Juliet walking from the left, and she is going up into y equals 1. Here's the Romeo walking from the right. He's going down into 1, and they both agree that the limit is 1, because they both gave the same y value. As they are walking left and right, they both point towards number 1. But the next situation of limit x approaches 3 of f of x is going to be different. See, 3 is going to be 3 times f of x. 3 times f of x is 3. 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 3 times f Juliet is going to approach from the left. That's a 3 minus. She's walking on this line right there, and her answer is 4. Because remember, limits are the y values. So the red one goes up to 4, and the Romeo goes to from the right, and he's walking down this one because that's the function available from the right side. That's his side. And he's reaching 2, right? X goes to 2 of, sorry, F goes to 3 plus, that's from the right, and the answer is 2. They do not match. Therefore, this answer here becomes does not exist, because limit does not exist, because the approach from the left and approach from the right did not give the same value. We actually use it to describe mathematically a cliff, or impulses, or things that are not of a continuous nature. And you will see much more of this in 2.6 next class, I hope, where you are going to learn about this discontinuities more. Now, your homework only consists of figuring out the tables of values. I'm looking at the book. Figuring out tables of values, and then also looking at the piecewise graphs to come up with, the limit and all this. So, believe it or not, that's 2.2, and we're going to take about 5-minute break, and then we're going to embark into much longer lesson on 2.3, which are techniques for computing limits. So if you need to refill your popcorn, and I don't know if you're definitely not talking and asking questions, so I'm not sure if you're watching this as a movie or which is the popcorn comment. But yeah, we'll be back soon for more of this.